We're going to start off still on the notes, and we are on number 18. Starting off this one, it says, which type of intermolecular force accounts for each of these differences? So they give us the answer here and saying that this one has a higher, what are we looking at, melting point, boiling point? Boiling point. So 65 degrees versus 6 degrees. So as far as attraction goes, this molecule has a greater intermolecular forces than this one does. And we have to figure out, okay, why? And what we're looking at here is, this is a methane. They both have a very similar structure in which you have a carbon with 3 hydrogens hanging off it. And then you have either oxygen or sulfur over here, and then a hydrogen here. And again, this one has a higher boiling point, meaning it has more attractive forces. And we have to say why. The reason this one is higher and has higher or has more attractive forces is very specifically because of what's going on right here. It has hydrogen bonding. So this one has, I'll just say, hydrogen bonding, where the other one with the sulfur in place has the same type of attractive forces going on here, except it's not one of those 3 atoms, nitrogen, oxygen, or fluorine, but in this case sulfur. And it's lower. So this one is going to be dipole-dipole, where this one's going to be hydrogen bonding. Let's look at this one. Xenon is a liquid at atmospheric pressure, whereas argon is a gas. So liquids, as I said earlier in the notes, have higher attractions than gases do. So argon is less, and why we can say that is we go back over to our notes. Xenon is a liquid, argon is a gas, and the reason this is a liquid is, of course, it has more attractive forces, and that attractive force is London dispersion. And the reason it's London dispersion is because of higher molar mass. There's more stuff. And when I say stuff, I mean protons and electrons and other atoms have an attractive force to each other. So different atoms are going to have the attraction between the protons and the other atoms, electrons. So this one I'm just going to put down is LD, London dispersion. Okay. Krypton has atomic weight of 84, boils at this temperature, where chlorine it has an atomic weight, and I'll make the comparison on those. Krypton has an atomic mass of 83.8, and chlorine, which is diatomic, is 70. So chlorine has a lower molar mass. Interesting. Where chlorine has a molecular weight of about 71, and it boils at this temperature. Now, if I'm not mistaken, this is actually a goof. This isn't supposed to be 1,000 and some. It's supposed to be 120, where this one boils at a much higher temperature. So chlorine boils at a higher temperature than krypton. So we have to figure out why. Why does chlorine with a lower molar mass boil at a higher temperature? And the reason for it is krypton, even though it has a higher molar mass, is spherical, where chlorine, being diatomic, is relatively, comparatively, more surface area. More surface area, more attractive forces. That is the reason for it. So we're still London dispersion, but it's more about surface area than molar mass. Something to be aware of. Okay, acetone. Boiling point here, where 2-methylpropane boils at much, much lower. Much more attractive forces. Let's take a look at acetone, if you didn't know what that was. So we've got hydrogens hanging out here. I don't want to draw them all in. That's simple. And then with acetone, we have a double bonded oxygen hanging out here. This is called a ketone, by the way. And then with the other one, what is it? 2-methylpropane. So very similar. I've got all these hydrogens hanging out here, but there's the methyl group. This is the functional group. So the difference is this one has a carbon hanging out here. This one's got a double bonded oxygen. And don't forget, you got these lone pairs hanging out here. This one has hydrogens. This one has a higher boiling point. It tells us that. And the reason for this difference on this one is because of the dipole-dipole that this has the potential for. These lone pairs on another acetone molecule, are going to be attracted to the hydrogens. So you have a greater attractive force, intermolecular force, for acetone that you don't have for 2-methylpropane. Because again, this has greater attractive forces, being oxygen and higher electronegativity, lone pairs of electrons as well. So more for this one, and we're going to call that again. I'll just write dip, dip. That is the reason why. All right, similar topic. We're going to do number 21. Which members of each pair has the larger dispersion forces? So here you have H2O and H2S. Which one is going to have a higher, very specific dispersion? So you may say, oh, boiling point, that's water, because it's got hydrogen bonding. You're right, but that's not what we're focusing on. Dispersion for this one is going to be based on the molar mass in this example. So the one that has a greater molar mass, sulfur has a greater molar mass than oxygen. Done. Looking at this one here, which one has a greater molar mass? That's pretty clear. 2 oxygens are more than 1. Finished. And then for this one here, silicon and germanium, it's like, I don't know, let's take a look at the periodic table. Pull this down. Silicon, germanium has a greater molar mass than silicon. Therefore, everything else being the same, germanium. Done. Okay, let's bounce back over to our notes. All right, we're just going to look at some general properties. And really, I think I'm just going to focus on one. We'll see. And this is pretty much just a definition. Is viscosity. You may have heard that before. Think about oil, maybe in your car if you know anything about that. Viscosity is the resistance to flow. So water has a pretty low viscosity, flows pretty easily. And something like maple syrup, molasses, those things typically flow really slow. They're very thick. They are very viscous. So it's related to the attraction of particles and molecules. Molecules. I'll say weight. So another class example would just be petroleum. So there's lots of different hydrocarbons. There's methane with 1 carbon, ethane with 2, and we can just keep dragging this out. As the number of carbons increases, you could have high viscosity, or you could have very, very low viscosity based on the number of carbons you put in the chain. So low carbon chain is going to be really easy flowing, low viscosity. The higher the number of carbons in this chain, eventually this stuff turns into asphalt. If you have 50 plus carbons in a chain, it's going to be a solid. Easy enough. I'll just mention this one. I'm not going to go far with it. Is surface tension. And this is the inner attraction. For particles or of particles for each other. So how attractive particles are to themselves. And one of the poster childs of this is water. So this is why raindrops are spherical. It's because the water molecules are very much attracted to each other. And in doing so, they pull together and they form spherical drops when they fall. because they are kind of attracted to each other. That's supposed to be a raindrop. As you fall in. And this is also why, for example, maybe you did this experiment when you're in middle school. You get like a penny and you start putting drops on it and see how many drops you can get to fall on it. And it really beads up on there because, again, the surface tension, these guys kind of attracting to each other. The idea is you also compare that to like alcohol, ethyl alcohol, and it doesn't do that at all as close. It stays really low and then eventually just spills over because the particles are not attracted to each other well at all. Okay, end of this lecture.